Welcome back, Calculus and Vectors class. Today we're going to talk about concavity and second derivatives and how they are connected to each other. So I won't go through every single point in this little introduction, but you should read through it and make sure that you're comfortable with it. But just really quickly, I'm going to kind of go over exactly how these two things are connected. So let's talk about the derivatives. Now we know that the first derivative has to do with the slope of the tangent. So we can see that as we are increasing, for example, in this one and this one, we can see that slopes of the tangents are all positive, and we can see on the other side, where they're decreasing, that they are negative slopes. As you look at the tangents, they're all kind of leaning downwards. So the big thing that we can see with the second derivative is as we look from left to right, how are those changing? So as we look at this one versus this one versus this one, we notice that although they're positive, they're going from very steep to kind of steep to not very steep at all. So we know the slopes are actually decreasing at that point. So it means that the rate of change is decreasing. We see the same thing on the other side, but this time instead we have negative slopes that are not very steep, so a very small negative number to a medium-sized negative number to a big negative number. So that number is still going down. So essentially what that means is that in both of these cases the slopes are decreasing. And this is a phenomenon that we call in functions concave down. You've probably heard of it before, especially with quadratics, but probably with any type of polynomial function, we see spots where it's concave up or concave down. And the opposite is true for concave up. So you notice how we have a very small, not very steep line, which would have a kind of a small positive number as a slope, then a medium slope, which is kind of a bigger number, and then a very steep one that has a much bigger number. So in this case, the slopes are increasing. And the same thing is going on the other side. That's a negative slope, that's very steep, so it's going to be a big negative number. And we kind of have a medium negative number to a small negative number. So what we notice is that when we have a concave up, that normally looks like this, then all of the slopes are going to decrease as we go left to right. And as it turns out, that all has to do with the second derivative. So when we have concave down, the slopes are decreasing, which means that the rate of change, remember the slopes are the derivative, slopes of the tangents. So as we look at how quickly they're changing, that's the second derivative. So in this case, the second derivative is actually going to be negative 0 in this, or it's going to be a negative number in this case. So it's going to be something less than 0. When we have concave up, it's going to be that second derivative is greater than 0. So we can actually use this information to help us determine a little bit more about functions that we're analyzing. So it turns out that that we can figure out when it's concave up or concave down as well. So let's talk about that really quick. So let's talk about how second derivatives and concavity connect to each other. So the first case, in a concave up part of a curve, if f prime of a is equal to 0 and f double prime of a is greater than 0, then f of x is concave up and there's a local minimum. Remember that the derivative being equal to 0 means that we have a minimum or a maximum. And then the second derivative determines if it's concave up or concave down, if it's a minimum or maximum. And remember, with concave up, it's always going to be a minimum because that's really the only way that they can fit together. And then the opposite is true if f prime of a is equal to 0 and f double prime, if the second derivative is less than 0, then it's concave down and there's a local maximum at that point, a f of a. And again, just like concave up and a minimum, concave down and maximum have to be together. And lastly, if f double prime of x is equal to 0 and f double prime of x changes the sign at a, there's a point of inflection. So essentially what a point of inflection means is it's a spot where we change from concave down to concave up. or vice versa. So sometimes we can have a second derivative equal to 0 and still be concave down to concave down or concave up to concave up. But whenever we have it equal to 0, it means that that's a possible point where it can change direction. Because just like when we were looking at maximums and minimums in the last lesson, when we have it hit 0, it's the only possible point where we can go from positive to negative or negative to positive. Because we know that when we have polynomials, the only way to cross over from positive to negative is to go past 0. So if we find the spots where it hits 0, then we know where it's going to switch from positive to negative. So that's where we can have this point of inflection. So I'm sure it's all clear as mud right now. So let's try an example, and hopefully it'll make a little more sense. So example 1 says for the function f of x equals x to the 4 minus 6x squared minus 5, find the points of inflection and the intervals of concavity. So there is a graph here. We won't worry about that for right now. Let's just try and see if we can find those points of inflection and the intervals of concavity. So we said to do that, the first thing we're going to do is we're going to find the second derivative and figure where it's equal to 0. So just to speed things up, we're all pros at differentiation now. So I've already written out the first and second derivatives. So what we're going to do is we're going to take that second derivative and we're going to set it equal to 0. So 0 is equal to 12x squared minus 12, or 12 is equal to 12x squared. We move the negative 12 over. We can divide the 12, so we get 1 equals x squared. And then we just square root both sides, and we get x equals positive or negative 1. So we can have possible inflection points at positive and negative 1. So we know that there's possible points of inflection. We don't know if they're actual points of inflection because we have to confirm where it's concave up and concave down. So let's try that right now. So to do that, we're going to do the same thing that we did in the last lesson when finding minimums and maximums. We're going to set up a factor table and we're going to analyze what happens here. So in this case, we're going to set up our function over 3 regions. We're going to have everything to the left of negative 1. So just to make this clear, we can have possible inflection points at negative 1 and positive 1. And we're going to do everything to the left of negative 1 to start. X is less than negative 1. And then we're going to do everything between negative 1 and positive 1. And then we're going to do everything to the right of positive 1. And to make this easy, let's break this down into factors. So we said that was 12x squared minus 12. We could write that as 12 x squared minus 1, which is all the same as saying 12 x plus 1, x minus 1. Just to help make this a little easier in case you don't want to try and do more complicated calculations. So let's write out those 3 factors and we're going to see what happens with each one in each region. So 12 is always going to be positive, no matter what. X plus 1, that's going to be, let's see, in x is less than negative 1, we pick a number smaller than negative 1. We could do number negative 2, that would be negative. And then for negative 2 minus 1, that would be negative again. So next one is, let's pick x equals 0. 0 plus 1 is 1. That's positive. And 0 minus 1 is negative 1. So that's going to be negative. And then we have x is greater than 1. So let's pick 2. 2 plus 1 is 3. So that's positive. 2 minus 1 is 1. So that's positive. And now, just to see what's going on, what the sign is on our second derivative. By the way, those, just in case I wasn't clear there, those represent our second derivative, the factors. So now when we multiply them together, for the leftmost region, we get we get, for this one here, we have positive times negative. The two negatives cancel and we're left with positive. And then for the middle region, we have two positives and negatives. So that negative is going to stay right where it is. And lastly, we have three positives, so it's going to stay positive. So that means, according to our definition with second derivatives, it means that in the first region, we have concave up, and then we have concave down, and then concave up. So that means that we do have a point of inflection on each of those spots because we go from concave up to concave down and vice versa. So we don't know exactly how this looks. We have to do a bit more work, and I'll go through all the steps in the next problem. But maybe it might look something like we go here, and then from here, that's where we switch from concave. Oh, whoops, we have concave up to start. So we're going to go like something like this. We don't know exactly what that y value is on that point of inflection, but we know that's where it changes to concave up. So as you're drawing that, make sure that you're really clear about switching the concavity to kind of be able to eyeball where it changes. So something like this. So we don't know exactly what the maximums and minimums are. We don't know what if there's intercepts, or if we don't know the y values of the points of inflection. But that's kind of mapping out what the concave up and concave down regions would look like. Something like that. So that should give you an idea. So now that we have that, let's try this one here. And this one, we're actually going to go and graph in full detail. So we're going to, this time we're going to do all of the elements that we can calculate for. So we're going to go piece by piece. Let's start with, we started this unit with intervals of increase and decrease. Let's start with those. By the way, I've already written out the first and second derivatives just because we know how those work. So increase and decrease. So what we're going to do is we're going to take f prime of x, sorry, and set it equal to 0. So 0 is going to be equal to 3x squared minus 6x minus 9. So we're just going to factor that. That becomes, let's common factor it. 3x, it's going to be x squared minus 2x minus 3. So that's going to be, let's see, it's going to be x minus 3, x plus 1. So that means that we are going to have local maximums or minimums potentially at x equals 3 and x equals negative 1. And to find the y values for those, we just put them into the original function. So the function f of x equals this one up here. And that's where we're going to take that. And f of 3, you can do the calculations yourself, but that would be negative 27. And f of negative 1 would be 5. So it means that we have those points the 3, negative 27, and negative 1, 5. And we can already plot those on our graph. So this is going to get to be a big graph. So let's go up by 5, 5, 10, 15, 20, 25, 30. Negative 5, negative 10, negative 15, negative 20, negative 25, negative 30. And then we'll go up by ones. 1, 2, 3, 4, 5 on our x-axis. Negative 2, negative 3, negative 4, negative 5. Let's start by plotting those points. So 3, negative 27 should be somewhere around here. And then we have negative 1, 5 right around here. So, first bit done. Now we just want to see, we can probably tell just by looking at it that it's going to be where it's going to be maximum and minimum, but let's confirm because you never know. Stranger things have happened. So let's make our factor table and study what's going on with that derivative. So let's break up our derivative f prime of x into its factors, which we got from this line up here. That's going to be, we had 3 times x minus 3 times x plus 1. And we're going to analyze it over each of those regions. So we want to know what's going on to the left of negative 1. We want to know what's going on between negative 1 and 3. And then we want to know what's going on to the right of 3. So for each region, you're going to pick a random value. Any one will work. And we're going to determine what's going on in each region. So 3 will always be positive no matter where we're looking. Or x minus 3. It's going to look something like this. And for x plus 1, we're going to look something like this. And hopefully you're good with finding those. If not, refer back to the last lesson. And to find the sign of our derivative, we're just going to multiply those together. So positive times 2 negatives is going to be a positive, then negative, then a positive, which means it's increasing, then decreasing, then increasing. So we're going to have a local max and then a local minimum. So that kind of confirms what we were thinking before. So now that we have that, that will be more information that we can rely on, that we can pull from when we're doing our final sketch of this. So now that we have that, let's talk about concavity. So we said to find out more about concavity, we're going to take the second derivative and set it equal to 0. So in this case, 0 is equal to 6x minus 6. Or we can factor out that, or we can set 6 equal to 6x, where 1 is going to be equal to x. So 1 is going to be a possible point of inflection. So now that we have that, let's confirm that. So we're going to take our second derivative, 6x minus 6. Let's factor it just to make our lives a little easier. 6 times x minus 1. And we're going to put that into a table and see what's going on over around to the left and to the right of that x equals 1. So let's set up our factors for our second derivative. And then x less than 1, x greater than 1. And let's see what's going on here. So 6 is going to be positive no matter what. For x is less than negative 1, pick a test value. Let's say 0. So that's going to be negative. And that will be, let's see, x equals 2. 2 minus 1 is positive. So in this case, we go from negative to positive. So according to our definition, we go from concave down to concave up. And lastly, before we leave our concavity, let's find the y value for our plane of inflection, since now we know it's a plane of inflection. So that's going to be f of 1. And we plug that into the original function, just like we did with the local max and min. And we get negative 11. So really quickly, let's plot that on the graph. 1, negative 11, somewhere like that. So that's most of the big information, but since we can do it, let's find a bit more information just to help us out. We know how to find intercepts. We haven't done this yet, but since we have all the tools we need to do a full graph sketch for a polynomial function, let's do it. So to find the x-intercepts, we're going to take that original function and set it equals 0. And that's going to be 0 is equal to x cubed minus 3x squared minus 9x. We can common factor that, so x times x squared minus 3x minus 9. And you can try if you want, but I can tell you right now, I'm quite certain that this one's not factorable. So you can use quadratic formula to help you out. So x equals 0, and for the rest, we're going to do x equals negative b plus or minus b squared minus 4ac over 2a. So that's going to be positive 3 plus or minus negative 3 squared minus 4 times 1 times negative 9 all over 2 times 1. And when you do the math on that, you should get something roughly equal to 4.85 and negative 1.85. So we have the three x-intercepts, so we can plot those. So we have 0, 4.85, somewhere around there, and negative 1.85, somewhere around there. And lastly, we can find the y-intercept, which is just, we set x equal to 0. So that's going to be 0 cubed minus 3 times 0 squared minus 9 times 0. Exactly like you have been doing since pretty much grade 9. And it's going to be equal to 0. That was for the y-intercept. And that was for the x-intercept. So now that we have that, let's plot that. And now we have all that information. So as we are going and drawing the actual curve of this, let's just review all the information that we gathered here. So we determined the maximum minimum, local maximum minimum, which were 3, negative 27, and negative 1,5. We determined the point of inflection, which was 1, negative 11. We determined the intercepts. And we also determined where it's increasing and decreasing and concave up, concave down according to our tables. So a couple things to watch out for. Just kind of watch carefully as I draw this curve. We start by increasing, and we said we're concave up at this point. So increasing and concave up. Sorry, I'm going to try and draw it a little bit smoother. Hopefully you can do it better with your pencil and paper. But so now we got to this point, and we said this is the local maximum. So now we start decreasing, and we're still concave. Sorry, this is concave down, we said. Still concave down. But at this point, now we switch to concave up. We're still decreasing. And then we're still concave up, but now we're increasing. And make sure you pass through every single point as you do this. And just before you leave this, you go through all your information, just confirm that that graph matches exactly what you found in your calculations. So now, what we've actually done here is we've actually done a full graph sketch based on all of the techniques that we have for graph sketching. And in fact, these methods will work on any single polynomial as long as you can take your first and second derivatives and set them equal to 0 and solve. You can actually find all this information for yourself. So just to quickly summarize here, a couple of pieces of information. I find this kind of my good general all-purpose go-to. The first thing I do, I just kind of go through. We can set y equal to 0. We can set f of x equal to 0. We can set f prime of x equal to 0. And we can set f double prime of x equal to 0. And all four of those things will give us different pieces of information. And in fact, everything that we found here kind of springs out of one of those 4 different calculations. So kind of keep that as your little in your back pocket just to help you out. And in fact, if you know those 4 things, you can gather all the information necessary to do a graph sketch of any polynomial function. Now, just before we leave this, let's try one more type of problem. We saw a couple of these in a previous lesson, but let's try this. So let's take this information. Let's see if we can sketch a possible graph. So the first one says the first condition is that f double prime of x is equal to negative 2 for all of x. So it means that it's always concave down. And in fact, there's only one type of polynomial that's always concave down. So in fact, that's going to be quadratic. Well, that's not true. It could be a cubic that kind of doubles back on itself, but quadratic will probably be the simplest thing to draw here. So let's take a look at the next part. F prime of -3 is equal to 0. So that means that we're going to have, we said that if the first derivative is equal to 0, it's going to be either a local minimum or a maximum. But since it's concave down, it means that we're going to have a maximum. And lastly, we have f of -3 is equal to 9. So that's just a point. So that's going to be -3, 9. So let's graph all that information. We have, let's start by plotting the point, -3, 9. It's going to be up here. And then we said that that's also the vertex of our parabola. It's a maximum, and it's always concave down. So really, in this case, that's all you need there, and that's your graph. For the next for the next graph, let's take a look at the information that we have here. So we said f prime of x is less than 0 when x is less than -1. So that says that we're going to be concave down over this region. Next part says f double prime of x is greater than 0 when x is greater than -1, which means we said that when f double prime of x is greater than 0, when it's positive, it means that we are concave up over that region. The next piece of information says that the derivative at -3 is 0, which means that we have either a local minimum or a max. We're not quite sure yet. And the same for that one there. So, looks like those are kind of our dividing lines there. So let's start by plotting those. Let's see. Let's just think in terms of our regions here to help us out. We said that for concavity, that -1 is a dividing line. And we said that, and then we switch on the other side. So it seems like, let's see, we're going to be concave down on this side and concave up on this side. So that means the only way that our two local mins and maxes can be arranged is that we have to have a max on concave down side, because we know that concave downs and maxes go together. And then we need to have a min down on this side. It doesn't really say much about specific points, but as long as we fit all that in, then we're okay. So we're going to have a max up here somewhere. We don't know exactly what the y value is, but that's okay. It doesn't really specify. It will still work regardless. And then we said that we are going to have a minimum at f of -1 or at +1. So now we just need to draw our concave down, concave up, being really careful to make sure that we switch concavity. When we get to that dividing line. So that's a little too early. Let's try that again. And that's about right. So something like that should fit. And that's pretty much all there is to it. So hopefully that makes sense. Try some practice questions, and I will see you in 5.4.